right, so I got a light ray coming in. And so I'm going to sort of picture I've got two strands of my light ray, like that. So I've got this wave coming in. And as we talked about before, when it enters a new medium, if it's going to slow down, it's going to bend. And that's not drawn as well as I would like. So, excuse my back. So if I have light that's being emitted from some source over here, I got these parallel lines coming in, and this is just to give some indication of the things that were released at the same time from the source. And it gets to a new medium, and then it's going to start working its way through here. So I'm going to concentrate on this little bit right here. I'm going to magnify it, and hopefully get a marker that will show. Right angle there. So I have a right angle. So this point right here is this point right here. This point right here is this point right here.
Where it bends.
Yes, the point it bends. So then I'm going to have the other part down here. Don't want it quite as bad as that. And at this point, I'm going to erase this and redraw it because the lack of precision there was messing with my head. That is a right angle there. That's better. So I have two different mediums here. And call this, yeah, we'll keep it more generic. I'm gonna call that, this is air over here. And this is some medium of N. Now, do that again. N1 and N2. This angle here is theta 1, and this angle here is theta 2. Obviously, these two lines here, or these two right triangles here, have this side in common.
Would that be the hypotenuse?
Yes, it would. And so I'm just going to give it something clever like, we'll just call it H. Ultimately, it's going to go away, so I can call it anything I want, but H for hypotenuse works. Now I've got a bunch of right angles here, so this is a right angle here. And this is a right angle here, and a right angle, too far there, there. So let's concentrate on this angle right here. If this is a right triangle here, and this is theta 1, this angle right here must be the complement of theta 1. In other words, whatever this is plus that, you have to add up to 90 degrees. And so what I usually do is just call it theta 1 prime. It's just whatever I need to do to get up to 90 degrees. So if that's 30 degrees, this would be 60 degrees. So just generic theta 1 prime. And therefore this angle here must be theta 1. Because these two have to add up to 90 degrees, and these two have to add up to 90 degrees. That is theta 1 prime. Going through a similar process here. If this is theta 2, then this angle right here must be theta 2 prime, the complement, which tells me that this angle right here must be theta 2. So those two angles are the same. Those two angles are the same. All right, so ultimately I know I want sine because, well, I gave you the formula yesterday or at some point within our past. So the sine of theta 1, well, what is sine anyway?
Complicated math equation.
See if we can come up with a simpler form of it. There's a complicated form for it, but I don't suppose you got the Taylor series or Maclaurin series when you do calculus? Do you Taylor series or Maclaurin series ring a bell?
No, I don't think we went over that,
Okay,
cause this was just applied calculus.
all right. Back to sine. What is it in terms of a triangle? Subpatilla.
Oh, okay, I understand.
Opposite over,
So if when I'm
Adjacent.
here, my opposite is this length right here. Which is, well, however fast that is traveling, so in that amount of time, so that is just the speed of the wave on that side of it times time. So that's gonna be equal to V1t divided by my hypotenuse. And sine of theta 2 is gonna be the opposite. This length right here, well, it's the same amount of time it takes for this to get to here as it does for this to get to here. It's traveling slower in this new medium, the way I've drawn it. So that would be V2, that should be a V1 there, V2t divided by h. And since I have h in common to both of them, I'm gonna solve for h and set them equal to each other. So from here, again, I can make anything into a fraction, so I have two fractions equal to each other. And I can just move stuff across the diagonal and it's still legitimate. So we have h is equal to v1t divided by sine theta 1. And down here, h is equal to, well, v2t.
T over sine theta 2.
Yep. So those have to be equal to each other, or the fabric of reality would completely unravel. Or I made a mistake. Well, time's the same, so I can just, it's both in the, they're both in the numerator there. I have the luxury of I can cancel those out. Speed, this is how fast light is traveling in that medium. And this is the whole idea that's in here, is that the speed of light is the speed of light in a vacuum divided by the index of refraction.
So the index of refraction would be VT divided by sine theta.
But the index of refraction would be C divided by V, or I wasn't quite sure where you were going. It felt like you jumped 2 steps there.
Okay, so how did you get if V is equal to C, or speed of light in a medium is divided by C divided by N, how did you get N?
Oh,
What is N?
for the N is called the index of refraction, and it can be found experimentally. Well, one by this, but there's a great deal of it that can be derived, if I'm recalling the E&M from grad school, but it's usually found experimentally. If you could measure the actual, try that one again. If you had the capability of, I can shine a light, you know, I have some medium here which light can pass through. I can shine a light here, it trips some sensor, so we gotta start timing. I have a sensor over here, so I can figure out how much time it takes to travel this path. I can then also put a sensor here and here, and figure out how long it takes to travel through the medium. And so I can get relative speeds and find the value of n. Or I can look to see how it bends when it enters the new medium. I feel like I haven't answered your question.
If the equation that we just did could find the time it takes for light to travel and whatever, then we can find n. Because we know what the light is in a vacuum.
Right. Usually n's just given for this course, but
Okay. But like, this equation that you just did, yeah,
v1 over sine theta 1?
Yeah.
I'm not done with it, I'm just,
I know, but
Okay.
eventually you could find the speed of light in that medium, right?
yes.
So you
Yeah,
can
'cause
find
you-
n
You could find n,
through that.
yes,
Yeah.
yeah. As long as you know one of the n's. All right, so we have a v here, so let's go ahead and plug that in. So this becomes c over
Beeping everywhere.
c over n
Yeah.
1 sine theta 1 is equal to c over n 2 sine theta 2. C's cancel out, we have two fractions equal to each other that we can then just do the reciprocal. And they cancel out, you're left with a 1. Just take the reciprocal of both sides, or multiple, bring them across the equal sign. And you end up with Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. And that's the equation that I wrote up last week. Questions? All right, let's take the next step. I think we did an example last time. I'm gonna do 2 examples, and that's gonna lead into the next topic. So if this is air and glass, it's going in at an angle of 30 degrees. It's slower in glass than air. What is this angle right here? Well, you need to know the index of refraction of air and the index of refraction of glass. That's textbook, comes in handy here, so. Page 680 in the book, if you're, or make a note if you don't have the book with you. Table 35.1 gives you index of refraction. Notice that glass has various, has more than one, depending upon the type of glass it is. And so we'll just go with ground glass, why not?
1.52.
Yep. And air, is it on the list?
I don't think
See, the air one is not on the list. Water is, but.
All right. Index of refraction of air is really close to the index of refraction of a vacuum. And so whenever you see air here, unless it's specified, it's close enough to 1. It's 1.000, I think then there's a number. And so 1 times the sine of 30 degrees is equal to 1.52 times the sine of theta 2. So that's 0.5 is equal to 1.52 sine of theta 2. And so sine of theta 2 is equal to 0.5 divided by 1.52. So theta 2 would be the arc sine of 0.5 over 1.52.
So you have to be in radians?
No,
No.
doesn't have to be. Because the 0.5 and the 1.52 are both unitless, and the ratio is also unitless, so it doesn't really matter. Degrees might be simpler, just because I think we're more used to degrees.
And also you're trying to find out the angle of that? Trying to find the angle of the sign?
Yeah.
Okay.
Trying to find the angle. And what do we get?
0.335.
I assume that's radians,
Yeah.
and then degrees. Could be something under 20.
17.98 degrees.
I got 19.204.
I rounded, so I put 53.7.
That seems like an awful big difference for just rounding. What rounding did you do?
Huh? I just typed in 0.335 times
Oh,
53.7.
that 0.335, was that ratio, or that was the arc sign?
That was the arc sign.
Okay. Oh. So I guess,
I got 19.204,
Right.
well, technically 19.205.
somewhere in there. Now notice that if it comes out, we don't need this anymore.
Yeah, 19.205.
Okay.
I just did it normally, just put in sign, arc sign of.
So crown, that was crown, yeah, crown glass. So it's starting in crown glass and being shot upwards at an angle of 40 degrees. It's gonna hit here and then go out. Let's put this in something with a smaller index of refraction. Ethyl alcohol. The light's traveling this way. So again, not expecting you to memorize these, because I definitely haven't. Ethyl alcohol, I just saw 1.36. And so it is 1.52 times the sine of 40 degrees is equal to 1.36 times the sine of theta 1, 2, whatever. What do we call this? Theta 3. So sine 40 degrees over 1.36.
I got 45.921 degrees.
Now, it makes some sense that it's not gonna be too far off of what we started with. Does make sense, it's gonna be bigger, not too much bigger, because the indices of refraction are not that far off of each other, 1.52 versus 1.36. Unlike over here, where we increased the index of refraction by 50%, here, we're decreasing it by, 10%.
So if they're the exact same, it's gonna stay on the same angle.
That's the ideal. In bulk and bore problems, you bet.
So say like, if it was water and alcohol, it'd be very similar, because the index of refraction are so similar.
Yeah, because water is 1.33, isn't it?
Yeah.
It's not even on that list there.
Oh, yeah, that's fine. Water? It's on the right side.
Oh, okay, there we go. Yep. Now, think of so as light enters one of these mediums, it's going to warp. Applications, if I'm trying to have some safety here, if I have thick enough glass or thick enough some substance, not air, that if someone, bringing physics around to violence again, from a sniper point of view, shooting someone through a window, you'd have to be dead on. If you do it off at an angle, then what you're seeing is a little bit off from where the target actually is. I don't know why I went to violence there, but it's physics, and I tend to do that sometimes. Not as
There's
bad as.
not like a whole lot of application for this.
And then there's the movie trope of smuggling diamonds in the water. I don't know if you've seen that. I've seen it in more than one film where you can't see the diamonds because they're in water. Well, the index refraction of water is 1.3. Index refraction of diamonds is
2.4. 2.42.
index refraction of glass, well, 1.52, not too far off of this. I would contend, and maybe it's just the skeptic in me, that in movies, they actually have glass hidden in the water, not diamonds.
And you just busted Hollywood.
It's like movies are a lie.
It's like movies are made up.
I know, that's
They're fiction.
shocking. Have you seen Fargo?
No.
At the beginning of it, they talk about this is based on a true story, and et cetera, and William H. Macy, who was in it, said, "You can't put that in there. People are going to believe that." And people making the film, the Coen brothers, said, "The whole movie's a lie. Why can't we put this in there? It's not based on a true story."
Mean they lie?
Why?